All right, so I'm assuming we're all logged in for our attendance. It is week 3. So this is the last week where it's easy, unfortunately. Week 4 is painful if you're not using StatCrunch, but it is completely possible to do the assignments in, less than 10 minutes. Week 5 is where it gets serious. But this is week 3. This is a face-to-face class, so we have a midterm, right, at the end of this week. So that midterm is in lieu of a quiz and consists of the stuff from week 1, week 2, week 3 homework. You don't have a midterm. Okay. But we cover the same stuff. So it's unfortunate that on the assignment there is only one question about this. And you may look at, once we cover it, you may say, okay, great, well, I don't know why that's there, just forget about it. But no. This is foundational for the rest of the semester, this concept. So we need to understand what's going on here very well. This is a neat tool. I believe there's 4 questions on it. Usually throws people for a loop. Especially if you are inclined to look at the help me solve this on the homework, the help me solve this button. You know what I'm talking about? You know what I'm talking about?
I know what you're talking about, yes.
There's a button that you can click on the homework that says help me solve this or view an example. And it walks you through either another example or it lets you try and step by step solve a similar problem. And surely you've heard the expression make a mountain out of a molehill. No? A mole is a really small animal, so I'd imagine they have small hills. But if we make a mountain out of a molehill, we're making a big deal out of nothing. That would be them in their guidance on how to do a percentile. But in almost every case, when you use the help me solve this or view an example, they've made an effort, it would seem, to be as long-winded as possible and to state everything just in the most confusing way that they could think of. So it's not helpful. We're going to want to do the percentiles like we talk about, which at the end of the day is the same thing. It's just it could have been said so much nicer. And then we have our last picture of the data topic. It's the 5-number summary and the box plot. Well, I bet you can guess what this thing is doing. It's 5 numbers that somehow summarize what's going on in your data. And it shows a different measure of spread than what we've talked about. Also, this box plot is a convenient tool for figuring out if your data has an outlier. An outlier is, if I had a bunch of randomly selected home prices, and and there was a bunch of them that seemed reasonable, and then there's one that's like $100 million house, that would be an outlier. Or if we're talking about salaries at the hospital, and I randomly selected a bunch of people, and it just so happens that the CEO or whatever's got picked, then they're going to have a salary much higher than anyone else's. So the box plot would help us to identify those data points which we might want to exclude from the data set, just depending on what we're doing. And then finally, there's this. This course does not do enough in probability, in my opinion. We should be doing a lot more here, but we don't. And it somewhat makes it more difficult, since we're not covering too much probability, it somewhat makes it more difficult in the future weeks, but we get by. So that's what we're doing today. Any questions before we get started? Z-score. Now, last week, when we were talking about the definition of variation, variation was equal to, in the numerator, you had the sum, we add up a bunch of stuff, the sum of all the deviations that were squared. So sum of all squared deviations. And then in the denominator was however many data points we had, take away one. And we'll get the opportunity to talk more about why it's the n-1 later. And I want to look at this numerator. It was the sum of all the squared deviations. What was a deviation? What does it mean in English?
Moving that straight away from the set point.
From what we expect, yeah. And so, how could I compute a deviation of some number? I've got a collection of numbers. There's an expectation of what a typical number should be, but then you've got this here particular number. I want to know its deviation.
It's distance from the mean.
Distance from the mean. It's the signed distance from the mean. So if it's below the mean, we're going to get a negative number. If it's above the mean, we're going to get a positive number. You can just say it's the observed value minus the mean. Right? It's the observed minus the mean. This would be some particular x value minus the mean x value. This is probably easy to remember. Observe minus the mean. 624430 is your code. Got it?
Thank you.
And the standard deviation, so that was what a particular deviation was. Each data point has its own deviation from the mean. And we said, well, we couldn't have an average deviation because it was always 0. So we have a standard deviation, which turned out to just be the square root of the variance. And that was as good as we could do because we built this variation. We started with an average deviation. That was just adding up all the deviations. But it turned out that this numerator was always 1, or always 0. And so we went through and just squared each one of them, and then took the square root at the end. So it's kind of like squaring something, then taking its square root, except for we added a bunch of stuff in between. It's as close as we could get to an average deviation. It's been what's called standardized, and this is our standard deviation. So we have this idea of a deviation, we have this idea of a standard deviation. Now the z-score is the ratio of those two. It's the z-score of a particular point. Every data point is going to have a z-score, and it is the deviation divided by the standard deviation. Once again, here is our code. So a z-score is a ratio of two deviations. It's the standard deviation on bottom, the deviation of that particular point on top. And since deviation was going to be called observed minus the mean, then you could say that this is the observed minus the mean over the standard deviation. It's just a number. It's just a number that you get which it adjusts this observed value. Instead of being in the distribution that's given by its histogram, it transforms it over to the normal curve. So if I have some histogram, it's approximately normal. There's my histogram. There would be some corresponding shape to the distribution. So it's looking like that, it's approximately normal. And it would have a mean that's, I don't know, we'll say 10, and it might have a standard deviation that is 3, something like that. And what happened, so this is my I don't need to label it. So then if I use a z-score to transform some data point, then it will put it will tell me its relative position on the standard normal curve. The standard normal curve is that curve where the mean is 0 and the standard deviation is 1. So I'll tell you how to know where the standard deviation occurs. I think I said it last time, but I'll say it again. But this distance right here is the standard deviation. And so an example, maybe, so the mean is 10, the standard deviation is 3. Well, what if I happen to go and grab the data point 8? I observe an 8. My observation is 8. And the mean is 10, the standard deviation is 3. So I would like to understand what is the z-score for 8. And what will happen is it will give me a number that would go on this horizontal axis. This is where the z-scores are at, is on this horizontal axis. And I will know, it will be in relatively the same position. However, it will be on the z curve, the standard normal curve, instead of this other curve. So this is the z-axis. And my computation would be the observed value minus the mean over the standard deviation. So you can see right there, 8 minus 10. That's going to be a negative number. That's the deviation of 8 from the mean. And it's negative because it's below the mean by 2 units. And so what I get is negative 2/3. And so it's about right there. Because negative 1 would be there. that one right there is about -1. The curve is symmetric. And I've indicated for you the distances from the mean, both on either side being 1, and that symmetry shows you that, right here would be the number 1, right here would be -1, and that's right where the standard deviation, the first standard deviation occurs. Okay, so how is it that I'm able to make my sketch where I know where the standard deviation happens? Curves in the plane, or any curve, could have what's called an inflection point, where it changes its inflection. And you can see that here. Everywhere in between these two dashed lines, the curve has this shape where it's downward. That's talking about its concavity. Everywhere in between those two dashed lines, it is concave down. But on the other sides of those blue dashed lines, it is concave up. And so when you just make the sketch, you can estimate right about where that point occurs. Everywhere in here it's concave up, but suddenly right there, or not suddenly, but once we get to that point, it will change its direction. And these points are called inflection points. And if I produce the mean right there, then this is the mean. And it turns out that this distance here is the standard deviation. It's a single standard deviation. Now, on the standard normal curve, where the mean is 0 and the standard deviation is 1, that would mean that this point right here, having a z-score of 1, is 1 standard deviation away from the mean. So you can take a data point like 8, and if the mean was 10 and the standard deviation is 3, and I produce the z-score, then I know that 8 is 2/3 of a standard deviation below the mean, because it's negative. It's completely evident here. 1 standard deviation below the mean is right there, and it's only 2/3 of the way to it. So the z-score has an interpretation as the quantity of standard deviations away from the mean. The z-score is the quantity of standard deviations away from the mean. That's your observation is. And we had said that we gave the empirical rule. It's called the empirical rule, where we could have estimates of the likelihood of some event occurring with this empirical rule. And so if I'm talking about the standard normal curve, mean of 0 and standard deviation of 1, we can phrase it in terms of z-scores now. So if for whatever observation I've made, it has a corresponding z-score, and if that z-score is between -1 and 1, then that event has a 68% of probability of occurring. Because 68% that's how much of the area this is. Underneath the curve is 100% of the area. And this part right here in between these two is 68% of it. And it's because that area under the curve, it turns out, will be interpreted as a probability. It's a probability because just like my relative frequency tables had to have the right-hand column add up to 1. Right? I started off with a frequency table. I added up the total observations. I got the total number of observations. But then I went through and just divided each one of them by that number and got a bunch of fractions. And if I added up all those fractions, I would get 1. So you'll be able to use that relative frequency table. We're just going to rename it probability table by the end of this class and see how the area underneath one of these things would be probability. But the z-score, since it's measuring the number of standard deviations away from the mean, if the z-score we see is between -1 and 1, well, that happens 68% of the time, and we're not surprised. Because that's a pretty big chunk. If it occurs between -2 and 2, it's even more obvious that it was likely to happen, because that's 95% chance that would happen. And then finally, if it's between -3 and 3, that's 99.7% of the area. So that means that of all the area under this curve, between -infinity and +infinity, 99.7% of it occurs right between -3 and 3. And it's a normal distribution. So things, if I can make a histogram out of my data and it looks like a normal curve, then probabilities of the corresponding events for your data set would be pretty much the same. Now, once again, when its mean is 0 and standard deviation is 1, that is the standard normal distribution. But there's lots of them. I mean, you might have an approximately normal distribution, but the mean is 120 and the standard deviation is 20. All right, that's pretty much what it looks like for blood pressure. So let's do an example where someone has asserted for us that mean systolic pressure is 120 and that the standard deviation is also 20. have a patient, so we have an observed value, and you check their blood pressure, it's 185. You seem alarmed because it seems high. And it seems high because that's what you've read in the books. But if this is the condition of our population, if these are the parameters of our population, 120 and 20, then we should, you know, and you're telling the patient, ooh, that seems bad, and they're like, no, it's fine. I was in a hurry this morning, and that's fine. I went for a jog just a minute ago. I jogged here to the doctor's office. That's the problem. And you want to know, how rare is this? Right? Not everybody's walking around with this happening to them. So let's get a Z-score. The Z-score is going to be the observed value minus the mean. Over the standard deviation. So that would be 185 minus 120 over 20. What'd you get? 3.25? Now the Z-score tells us how many standard deviations away from the mean this observed value is. And that's more than 3 standard deviations, right? 99.7% of the time, when we check their blood pressure, it's going to be within 3 standard deviations. So then this patient falls outside of what happens to us 99.7% of the time. It almost will never happen, in other words. And since it's such a rare event, that should correspond to the degree of alarm we have, right? There won't be any of this business like, oh, it's just barely outside of 3. I mean, even getting to 3 is pretty phenomenal. And if you're on the other side of it, forget about it. That's 0.3% of people. So that's 3 out of every 1,000. And they're trying to tell you it's fine, it's fine, it's fine. And you would know mathematically that it just can't be. In fact, it's very, very, very bad. Or someone could, you could measure a different patient and get 138. And you're like, it seems high. And if that happened to us, we could calculate a different Z-score. So it's within plus or minus 1 standard deviation. That's pretty normal. That's pretty normal. That's pretty normal. In fact, the closer the closer this number is to 0, the closer your observation is to the mean. So
is this how they figure out the dosage, like the dosages and like lab values if they're all normal? So would this method be, like let's say they have a lab, like their glucose level is 3,000. So would this be a way to see if it's in range
Yeah.
They would,
But, so it's
Or
a
not
little more
very-
complicated. They would want to
Yeah.
establish what the proper range is.
yeah, yeah.
Okay. And we will do problems exactly like that in week 5. To establish that proper range is called a confidence interval. So like if you get a blood test or do a blood test or something and it comes back with, the normal's between here and here. Those numbers came from looking at a sample of people, determining what is the mean that we get from that sample of people, but then we have a margin of error that we calculate, and that margin of error depends on how likely do we want our answer to be correct. And we can establish an interval and say we're 95% confident or 99.7% confident that the real number for what a normal glucose should be in this range. Well, then if somebody has a number like that that's way outside of it, you can find the probability of being that far away with this method. Okay. Now, let's look at this 0.9. Let's draw a picture. So I've got my normal curve here, standard normal curve. I took that observation that I had about the patient, and now it's been standardized, and right there is 0.9. And the first standard deviation is right there. The point of wanting to do this is I'm working my way up to it, but what will happen is that 0.9 being a number on, it's a score, it's a number on the horizontal axis, but it corresponds to an area under the curve and above the axis. And all you would want to do is just project that point straight up to the curve, and then maybe I can figure out somehow what all of the area over here is. Just like there was a way with that empirical rule to know you had 68% and then 95%. We're going to have a way to figure out what this area here is. Now you see how all this area is on top of the region of numbers down here that are less than 0.9. Then whatever that area is would be the probability. It would be the probability that if you picked some other random patient, that you would get a reading, that you would get a z-score for their blood pressure that was less than 0.9. And that's what we're working up to, is this understanding of the area under the curve being a probability. And that will be what we do the rest of the semester after today, is areas under the curve. Areas under the curve, what do they mean? How can I interpret it? Stuff like that. The z-score also will allow you to compare things that aren't normally comparable. We can compare things that aren't normally comparable. I don't want to do my usual example because I don't like it. Let me ask you if you've heard this saying: you can't compare apples and oranges. What they're meaning is you can't compare apples and oranges because they're just materially different, right? But it turns out that you can. I don't want to do that example. Maybe I'll do. Okay. I just wanted something more extreme to show off what's happening. I have a bicycle. Here's my bicycle. Okay. And I've always felt that this bicycle was kind of heavy. They could have done a better job of getting lighter material. I always thought it was pretty heavy. And I weigh this bicycle, and it turns out to weigh 25 pounds. It's pretty heavy for a bicycle. And then I do a little research, and bicycles in this category of this style and wheel size and everything, I do some research and I find out that they have an average weight of, that they have a mean weight of 12 pounds with a standard deviation of 6 pounds. I'm just making this up. And I'm thinking, dang, my bike is really heavy. But then, there is but then I'm doing some let's see. And then so I go to work, and my job is that I push a wheelbarrow full of stuff for my job. It's a wheelbarrow. Some days it's dirt because we're doing gardening. Some days it's full of rocks, and some days it's got feathers in it. Some days it's got some days it's just filled with concrete. And I push the wheelbarrow every day. And one day at a particular job, they've got it filled with something strange to me. It seems very, very heavy. This load that I'm pushing. And so I push it across the scale. It weighs 400 pounds. It weighs 400 pounds that day. It seemed really heavy to me. It was very hard to push around. And but I'm such a diligent worker, I've kept I've weighed all of my loads, and I can know the mean and the standard deviation of all the loads I ever pushed somehow. Probably never happens, but pretend it did in this case. So, because on some days I'm pushing around pillows, and on other days I'm pushing around rocks, then that mean gets skewed down by those lightweight loads, and maybe the mean weight is only 200, or we'll say 190 pounds. But there's such a wide variation in what I'm pushing from day to day, the standard deviation is 130 pounds. And the question now would be, well, which one was heavier? Was this load that I was pushing that right there that weighed 400 pounds, was it heavier than my stupid bicycle? Well, it's not enough to just it's not enough to just say, well, this was 400, so it's clearly heavier. I mean, which one was relatively heavier? Was this load that I'm pushing heavier than my bike was heavy? Clearly, the bicycle it weighs way more than the mean, so it's heavy. And this load weighs way more than the mean. It's heavy. They're both heavy. But if I standardize each of these observations, I observe this, I observe this. If I standardize each of them to get z-scores, then I can compare the z-scores and see which one was further from its own mean in terms of standard deviations. So for the bicycle, our z-score is 25 minus 12 over 6. And for this wheelbarrow load, the z-score would be 400 minus 190 over 130. Z-scores will always round up to 2 decimal places. So if you did that in your calculator, you get 2.166666. Well, to 2 decimals, that would just round to 2.17. So this bicycle, it is heavy, but it's just 2.17 standard deviations above the mean. For my load in the wheelbarrow, I must have been feeling wimpy that day because it is only 1.62 standard deviations above the mean. So insofar as bicycles go, the bicycle is heavier than the heaviness of this wheelbarrow load. This one is only barely 1.5 standard deviations above the mean, but that was more than 2 standard deviations above the mean. So, yeah.
So then I know the definition of the word, then what does this mean, since logically it doesn't weigh more? What is it giving us? What information are we getting?
It weighs relatively more.
Relatively.
Relative to the other members of its population, it weighs more. Like maybe one day, maybe I can have an example where it's, I'll select some people that are genetically, they weigh a lot less. So I'll have like some Chinese patient, and over here I'll have a Samoan who are notoriously much bigger. And I wanted, and they're both seem to weigh more than the average for their ethnicity. But which one is, and the Samoan will weigh more, always. But which one weighs relatively more than the other members of their populations?
Okay.
See what I'm saying? So if you were Samoan and the doctor says, well, you're overweight, you might want to know how much. You obviously would not compare your status to to a group of people that are almost always way less than people on the other side of the world. Yes?
So is that kind of like, for like the age, the weight, they kind of have like charts, you know, where it's like, you should be this. Is that kind of like it, or is that different?
That's different.
That's different.
That's going to be like we're going to do that exact thing here in a second.
Okay.
Because on that chart, it's giving you. If I had a chart that was like a different one for each year, that, like, you know, the child grows up and they, you know, here's a bunch of list of weights, and if it's like right in the middle, then, you know, you're average, right? It's the same in that regard if I froze it at one particular year, but as soon as I start to consider more and more years. So I guess it kind of could be in the sense that if it was a list of 100 weights, then the one that's right in the middle over here and the one that's right in the middle over here would have the same z-score of 0, because it's right in the middle. Yeah. That's a percentile chart. We're about to do that. Question? Z-score allows you to compare things that would normally be incomparable. Now, the question that they ask on the homework could really be done without a z-score, but they go ahead and have us give it a try. So you've got two persons, two men. The tallest living man at some point in time, and then the corresponding shortest living man. Each of them are far from the mean, right? And if I encountered the tallest living guy, I'd say, you know, dang, you're tall. I probably wouldn't say that to the short guy, but you could replace that word tall with, you can replace everything I said with, wow, your height is far from the mean. And for the shortest living guy, you could say the same thing. Wow, your height is far from the mean. And if we find their z-scores, we can figure out which one was further from the mean. How many standard deviations each of them were from the mean. If we do that, then we'll know whose height was more extreme. Whose height deviated more away from what we would normally expect. So, the z-score for the tall guy, my numbers would be 243 minus the mean, which is 170.65, over the standard deviation, 7.55. It's in centimeters. So the tall guy was nearly 2.5 meters tall. That's not that tall. The short guy had a height of 117.2 centimeters. Now that is less than this mean, so when I take their difference, I'm going to get a negative number, and I should, because his height is below the mean. Let me see what I get. So this tall guy had a z-score of 9.58. And the short guy had a z-score of minus 7.08. I mean, normally they would seem incomparable. You would have the tall guy, you'd have the short guy, it'd be like, okay, whose height is more, whose height is, it's not just further from the mean. If I calculate if I calculate the distance from the mean, then you're going to get just its deviation. It has to be in comparison to the standard deviation. That's why we divide it by the standard deviation. Because if the deviation that we got was the same number as the standard deviation, your z-score would be 1. And if the thing that we observed was the very same as the mean, then your z-score would be 0. That z-score, being a quotient of the deviation to the standard deviation, is just building us this fraction that can tell us, because the standard deviation is down here, then whatever number comes out up here divided by that will tell me what proportion of these standard deviations we encounter. Well, this guy was about 7 standard deviations below the mean. It's like instead of counting by 1, I want to count by standard deviation. That's all it is. He's 7 standard deviations below the mean. This guy is 9.5 standard deviations above the mean. Tall guy is more extreme. The tall guy is taller and the short guy is short. So z-score for the tallest living man was 9.58, and for the shortest man it was minus 7.08. Don't forget the negative. So the tallest man had the height that was more extreme. That is the z-score question. How do we feel? That was a lot of talking to get one question, but it's important. So, and like I was saying, the z-score being a ratio of 2 deviations has these 2 important observations. The first of which is that if my observed value is equal to the mean, then my z-score is 0. That would correspond to not being any standard deviations away from the mean, because you're equal to the mean. Of course you're not any standard deviations away from the mean. Likewise, if my deviation was equal to the standard deviation, then that's a z-score of 1, because it's a fraction and the number on top and bottom would be the same. If we talk about counting by, if you count by 1, usually, well, it's 1 in this sense. We're counting by this kind of a 1. And this kind of a 1 is to count by standard deviations. Because if these two numbers are identical, then that's got to be 1. Same on top and bottom. I mean, you could keep going with, you can make like another observation here that these are the most important ones, but if you realize those two of them, then you could say, well, if my numerator was 2, or rather, if you want to say, if my deviation was 2 times a standard deviation, meaning that my number on top was twice as big as the number on bottom, I measure the deviation, okay? If my standard deviation was 3 and I measure the deviation and get 6, that's twice as big. That's a deviation that would be twice a standard deviation. And your z-score would be 2. And it just goes on and on and on. Whatever number you want to use, then at that point you can. I mean, you can see that here. If I just divide both sides by standard deviation, you get 2 on one side and you get z on the other. All right, it's break time. Let's take 10. And when we come back, we're going to switch over to percentiles, which there's 4 questions on that. Okay, need a few. So,
So, I basically got this with the different numbers, of course, but mine came out being the short man, height to height, that was more extreme.
okay.
So how would I be able to know the differentiate between the smaller and the shorter?
Which one's further from 0?
Oh, well, the negative 14.15, because the other one's 10.24.
So that one's more extreme. Because that number you're looking at measures the number of standard deviations. The negative is only telling you if it's above the mean or below the mean. Well, once you use your z-score, your mean has been like reconfigured to be 0. So that way, when you look at the z-score, it just is the number of standard deviations. Yep.
So, here,
I just heard.
all right, thank you. I just remembered right now, because I'm watching the picture right now.
I got it.
Thank you.
Okay, it's there, all right.
Yes, yes, thank you.
was just calling to inquire how much an eye exam would be without insurance. 88, okay, and then plus the purchase of the eyeglasses. Okay, sure. Alright, and then do y'all take walk-ins or do I have to make an appointment prior to? Okay, perfect. And y'all are open until 6:30? 6 o'clock, okay, perfect. Thank you so much. Bye.
Percentile. You're probably already familiar with the percentile, just didn't know it. Not a percent, it's related to it. Percentile is a score. It's a score. I'll call it P. P sub N, no, not N, P sub T. So you get this capital P, and then, so we can know which one we're talking about. It's indexed with this lowercase t. So T would be some number like 40%, or just 40. It's a score, P sub T, so that this percentage of all other scores are less than P sub T. So if a bunch of people take a test, like maybe the SAT, for example, then when you get your score report back, you'll be given some numbers, and among them would be percentile score. And that helps you gauge really how well you did, compared to other folks. And if I got back this score, this number, this thing is a number, and if I got that back as my percentile score, then what I can know is that this percentage of people scored less than me. So maybe I got back a percentile score that was 90%. let's say for grins that I got back a percentile score that was 90%. Or not 90%, just 90. Then my conclusion would be that 90% of other people scored lower. So in some cases, it could be good to have a high percentile score. In some cases, it'd be bad. You know, it's on a test. It's probably good to have a. It is good to have a high. Well, it's an academic test. It's good to have a high percentile score if it's a. Your cholesterol test. It's probably not good to be in the 90th percentile. So. That's it. That's the definition. Now, it has to be less than. Not less than or equal to, strictly less than. Strictly less than. Can't be. Well, this would be an easy problem if we always had like that chart with 100 numbers, 100 different scores. And so maybe it's, I don't know. Bicycle weights again. So then, I went out and randomly selected 100 bicycles. And not just random selection, but I made sure that my sample could cover would match the demographics of all such bicycles. And there's some out there that were really light. But by the time I got up here to number 35 on the list, it was, something like this, maybe. And then by the time I got to the end of the list, there was a 40-pound bicycle made out of thick steel or something. So if my data set had 100 data points, there's two kinds of questions that could be asked. You could ask the question like, you could say, give a bicycle weight that is at the 35th percentile. In other words, P sub 35 or I should say 36th percentile. Then piece of 36 no, I had it right at the beginning. Sorry. Okay, well, there's 100 numbers on the list, so it should be easy for us to figure out which one of these numbers has 35% of the other weights less than it, right? I need to know which one of these weights is at the 35th percentile. That's what P35 is. The little subscript down here is telling you to find the weight that has 35% of the other weights below it. Which one would you pick? $12. No, not 12. It has to be strictly less than. Huh? No. If I go right here to the 12 pound, it's number 35 on the list. There aren't 35 that are below 12. There's 34 that are below 12. 12 would be at the 34th percentile. This one is at the 35th percentile because how many are less than this one? There's 35 that are less than this one. Remember our definition. It said strictly less than. So it can't be equal to and work out for us. Right? This is 35 numbers out of 100, so that's 35% of the data. 35% of the data is less than this number. So it's 12.5. %9% of the data, I'd have to look at all the first 99 numbers. Then the one that's at the 99th percentile is 40. Because 99% of the numbers are less than it. You can't get to the 100th percentile by this definition. Because you can't score more than you scored yourself is the issue. Right? So if you have the heaviest bicycle in the world, it would be at the very bottom, but it can't weigh more than itself. So you would always have to look at the one before it and say, all of these are heavier than my heaviest bicycle. And when there's 100 on the list, that's the easiest case. of figuring out the percentile. If it's a number different than 100, that's when it's more tricky. Here they have radiation levels of 50 different cell phones. I can click the box, and I can see all 50 of those radiation levels. And fortunately, they are in order. They're rows of 10. 5 rows of 10. Okay? And what do they want from me? They want me to find the percentile corresponding to 0.81, to the radiation level 0.81. Now 0.81 is right there. .81 is right there. And these are sorted in order, right? So I could count them off, 1, 2, 3, 4, blah, 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 all the way down, 49 and 50. So which one is 0.81? What's the 10th one? It's the 10th one. So how many data points are less than it?
9.
There's 9 out of
100. Oh, 50.
Out of 50. So you would have 9 out of 50 data points less than 0.81. That's 18%. Nine out of 50 of the data points are less than 0.81. So you get 18%. That means that 0.81 is 0.81, that thing right there is a piece of 18. It is the score for which 18% of the data points are less than it. And so my answer is that it is at the 18th percentile, just the number 18. These are all the data points that were less than the one they asked me about. 9 out of 50. So I just compute, what is that number, 9 out of 50? Well, it's 0.18, which is 18%. I didn't really do that. What I really did was just say, well, I know it's 9 out of 50, and now let me multiply by 1. And now the denominator is 100, the numerator is 18. That's 18 out of 100, it's 18%. Are you all able to get yours? No? What's wrong with yours, Esther? You don't get it?
No, how did we get the 18?
Say again?
How did we get the 18?
So they asked me to find the percentile score for that observation. And I look at that observation and I see that my entire data set is in order, right? And so I can count them off. This one was number 1, this one was number 2, 3, and so on. And this one that I'm interested in is number 10. Okay? So that means there was 9 data points that were less than 0.81. And I just asked myself, well, there's 9 out of how many? 9 out of a total of 50. And when you do 9 divided by 50, you get 18%, 0.18. Yeah. They have another one for us to look at. Same type of question, radiation level. Find the percentile corresponding to 1.44. There's 1.44. Now I know that there's a total of 50 numbers there. 50 radiation levels. But how many radiation levels are less than 1.44? Well, it'd be 10, 20, 30, 40. 1, 2, 3, 4. 44 of them are less than that one. And that's 44 out of 50, which is 88%. So that means that this score right here could be denoted P sub 88. It's the score at the 88th percentile. Getting it? Well, the next 2 questions, they change it on you. They ask the inverse question. Here they want to know not what is the percentile of some score, they want to know which score is at some percentile. And it's the score P sub 40. P sub 40. But once again, all of the data points are in order. That's crucial, that they be sorted least to greatest. And so I'd be interested in which one of these data points has 40% of the other data points below it. So I would want to know which position out of 50 would do it. Which position out of 50 is going to come out equal to 40%? So I'm interested in what happens at position 20. Now my answer is not necessarily the number that's in that spot, in the 20th spot. In fact, it usually does not. Because whatever number is right there in that spot only has 19 other numbers less than it. That's not 20 numbers. I need to have 20 numbers underneath whichever one I pick. But I have a problem here because this one does have 20 numbers less than it, but it's equal to the 20th one of them. Yeah.
How did you come up with the 20 for X?
Solve that equation for X. Yeah. Yeah, you solve that equation for X, and that's it. 40% of 50 is 20, right? Now, I'll tell you, there is no standardized way. Unlike other things in statistics, there's no universally agreed upon way to do this. Some definitions let it be less than or equal to. In the latest revision of this book, they've changed it to just be less than. So even they themselves change what they're doing over time. Some people would say, well, the answer to P40 does not necessarily need to be any one of these data points. It could just be a number. I could just make it be 1.115. 1.115 is bigger than 1.11. And less than 1.13, so it would have 20% of the, it would have actually more than 20% of the data points less than it. It would have 22% because this number matches. So I'm trying to predict what the author of this book would have wanted. If I type in my answer as being 1.11, then it would certainly have 20% of the data points less than it. But this score is also 1.11, and it only has 19 data points less than it. So then that could give 1.112 percentile scores that would be equivalent. It could be piece of 40, or it could be piece of 38. So the conundrum here is that piece of 40 would have to equal piece of 38. Piece of 38 because 19 over 50 is 38%. However, if I put in a number, like if I was to put in 1.13, then that would be automatically more than P40. So I'm going to go with 1.11. I'm not 100% confident that it'll be right. We'll see. So their train of thought must have just been, let's apply the definition strictly, and we don't even care. These could have all been the same number. Every number on this list could have been 1.11. And they could have asked me, what is piece of 40? Well, I would have went down here to the 21st number and been able to argue that there was 20 numbers out of 50 that, well, no, I couldn't say that. Maybe the problem is what I'm not saying. So what I usually say is, I want 20 numbers to be less than this guy. But I really don't have that here. I have only 19 numbers less than that one that's in the 21st spot. And you wind up with this happening. So, like I said, it's not universally agreed upon. It's not clear cut. This is like the reasons why, you know, because you could have your data set have repeats. Here's another repeat. Same thing will happen there. And that's another repeat, and another one, and another one. The majority of that stuff is repeats. I wouldn't be surprised if your question 4 had repeats, where you had to deal with that. But it seemed that our same strategy worked. They were talking about piece of 40. That corresponds to the 20th position. And so my answer was whatever was in the 21st position. Did y'all get number 4?
I feel like I get it, but I don't get it. I get it in the sense that I understand what numbers I need to plug in to get the answer, but I don't get what I'm looking at. What are we determining? .11. What is that saying?
1.11 is a radiation level. And 40% of the other radiation levels for all the other cell phones were less than it. If I go to the pediatrician's office and they say your child is in the 60th percentile of weight for their height, then that means that 60% of other children had a lower weight than mine for their height. If I go to the doctor and they say, well, your cholesterol's in the 90th percentile, and 90% of other people have lower cholesterol, that probably is not good. But if you're at the 50th percentile, you're at the median. You're at the median because that's the number in the middle, right? You're at the 50th percentile. So in other words, you should interpret piece of 50 is approximately the median. Here, I'll do one more on number 4. So again, it's the radiation levels. Find piece of 30. Okay, so I'm going to want to know which position is at the 30th, which position is 30% of the way through 50. So the 15th data point, that's number 15. So I should go right here to number 16. Just so happens to be the case, they're the same number, but that's the one I'm going to use.
What if your x is a decimal?
That's in the next problem. You round up. So here they've said for me to find the percentile of 25. So which position out of 50 is at 25%? Well, that would be position 12.5. But that doesn't make any sense because they're only integers. But if you tried to round down, then you would automatically not be capturing 25%. Because if you look at the 12th position, the 12th position out of 50 would only be the 24. You would only have, so if that's position 12, then this number only has 24% of the data points under it. So I got to go here. That one has 13 numbers under it. That's 26%. But we have to err this direction. So the 12.5 has to, I get a decimal for that position, I have to round it up to 13. And then I go to the 13th spot. Okay. That's the number in the 13th spot. But then this one's my answer. Because it's the one that puts at least 12.5 numbers under it. And again, this would be where some people would do it different. Some books would say, well, no, you don't go to 0.93 because that would be 26th percentile, and that's too big. And they would say the more correct answer would be 0.925. Because 0.925 would have all those 13 less than it, but it would also be less than 0.93, so that it could have a different score. But these people don't do that, so 0.93. Unless they change something again because of the new addition. Let me think for a second. So the 25th percentile would be position 12.5. We used to have this rule where we always rounded up, but that must have been because the definition was less than or equal to. If you don't round up and you instead
What is 0.92 be
0.92 would be in position number 13. However, how many data points are less than 0.92? Only 12, which is the 24th percentile. And that's the problem. So I wonder here if I could get away with an answer of 0.925. I'm thinking it's going to take 0.92 or 0.925, and that they didn't like my 0.93 because it's technically the 26th percentile, and that just makes it too big. So I'm going to try 0.925, and if it doesn't like it, I'll put 0.92. If that's not it, then I don't know what the answer is. I want to try this because I want to know if it takes it. If it does, then that would be a more clear way to explain what to do in this case. Because your percentile score does not need to be one of the data points. It just needs to be a number. And that number there, 0.925, would fit in between 0.92 and 923. So it would be like as good as we could, it would be as close as we could come to going to the 12.5 position and then one more. I'm gonna give it a shot. I'm not expecting it to take it, but we'll see. No. So then our only choice is 0.92. So.
Oh, no, I'm trying to resume.
So this is different than the way they used to do it, but it matches with them changing the definition from less than or equal to less than. Because then here you would, when you got 12.5, you would round down. Even if you got 12.9, you would have to round down to 12. And then so we would come right here to this spot and say that's the position we're interested in, so then that's our answer. Now 0.92 really only had, 0.92 is really at the 24th percentile. But because there's 50 numbers in the list, all of the, you're gonna have a bunch of overlap, right? P24 is always gonna be the same as P25, and you know, P of any even number, you know, P of 6 is gonna be P of 7. Just because you can't get 7% of the data points less than it, not until you have 100 data points. What's up?
I had pretty much the same problem, same equation. And I got the answer right, and I didn't do it the same way. So now I'm confused. If I get this problem, I'm gonna get it wrong.
What you did?
Well, my n equaled 37.5. Between 1.31 and 1.32, I chose 1.31 because that number falls between 37 and 38. And I chose 1.31 and it said it's right.
I got the same one and I put 1.32 and I still got it right. But
So
I
it's-
rounded up to the 38 spot and then put the 38 spot.
So it's like a either or? Is that what it is?
It accepts multiple answers, but like I said, it's hard to predict what they're going to take if they're changing the definition all the time. And they're just changing it in response to other people complaining because, you know, somebody somewhere else had their complaint heard that they did it different their whole life, and you're going to change it. And like I said, it's not standard.
Okay.
As long as you, I mean, if you're reasonably close, in practice it'll be fine. But to get it right, to predict whatever they're thinking, then we would have to adopt my round up rule to round down. And if you round down, then it would always work. You would just go to the 12th one, and then the next one. And then at least that answer would be correct. However, they should still accept answers like 0.88, 0.89, 0.90, 0.91, and any of those numbers in between there. Because they would all do the same thing as 0.92 in that they have 12 data points underneath it. And you could argue that if I had a number, you could argue that if I said that my answer should be 0.895. 0.895 is exactly halfway in between those two. And so even if in the future we started putting more numbers into this table, then it would be a pretty good chance that that if I scoot my answer all the way up to 0.92, then you for sure get all 12 of those data points. If I choose a number that's in between those two, I still get all 12 of those data points. But if this chart were to expand to have 100 numbers, some of them would be less than that, some of them would be bigger than that. And if I elaborated it to have 100 numbers, I might exactly get the 25 out of 100 numbers to be less than that. Anyways, it doesn't matter. Did we all get these 4 questions? Okay, good. That's percentile. So when you get a decimal,
Yeah.
round down. All right. Up next is the 5-number summary and the box plot. Now, so the 5-number summary is obviously 5 numbers. It is the minimum, the maximum, Q1, Q2, and Q3. Q is for quartile. Q is for quartile. So it's a quarter of the data, and another quarter, and another quarter, and another quarter. It'd be 4 quarters. That's 100%, right? So all the data in between here is the first quarter, and then here's the second quarter of the data, and here's the third quarter, and then that's the 4th quarter of the data. 4 quarters is $1, so that's all of your data that's in each quarter. And then the Q1, Q2, and Q3 are the quartiles, so they're right at the edges of those quarters of the data. Q1 is, if not equal to, then really close to piece of 25, and Q2 is essentially P50. But even that had a different name. That was the median. And Q3 is essentially P's of 75, the min and the max, or whatever they are. Now, I put the equal symbol, but they're not really equal. The percentile definition is not clear. The quartile definition is clear, unmistakably clear. So they're largely the percentiles, but more correctly, we will compute Q1, the median, and Q3. Now Q1, if I take my data, I've got some data. If I break it in half, the lower half and the upper half, then Q1 is the median of the lower half, and Q3 is the median of the upper half. That's why they are unmistakable as what their answers could be. And if you look at my data here, I've got 20 data points, and they are in order. That's convenient. It's required in order to do medians, right? And so I can figure out what my 5-number summary is because my data has been put in order. The minimum number is 122, and the maximum here is 160. Now I'll do the median. The median of these 20 numbers has got to be the average of 139 and 143. So that median should be 141. Now, the data is already organized in such a way that we can easily see I have the top row and the bottom row. So it's already broken into 2 pieces. So I can go grab the median of this top row, and that's Q1. Yes?
How do you get 1?
How do I get what?
141.
141, that's the median, because there's 20 numbers here. So the 2 numbers in the middle are numbers 10 and 11. This is the 11th one, this is the 10th one, and I take the average of those 2. Now there's 10 numbers in the top row, so if I go to positions 5 and 6 and take their average, that's the median of the top row. So that's number 5, and that's number 6. The number that's right in between them is 132. So 132 must be what Q1 is. It's the median of the top row. On the bottom row, I'd be looking at these two numbers. Those are the two in the middle on the bottom row, and their average is 148.5. This is the 5-number summary. It summarizes what happened in my data set using these things called quartiles, which we haven't seen until now. Now, there is another measure of spread that we didn't talk about last week because nobody asked any questions on it, and it's called the IQR. The IQR is a measure of spread. It's the interquartile range. It's the distance between Q3 and Q1. You can see it readily in our box plot. Because the box plot, if I can sketch a box plot right here, what I'll do is I'll just make a horizontal axis, and I'll try and be careful with my tick marks. I want to be able to plot all of these numbers. And so I won't put any more tick marks than what's needed just for those. So I'll start here at 120, and I guess I'll just go by 10. So 120 and then 130, 140. I need to do better than that. I can make it bigger. So there's 120, 130, 140, 150, 160. And to make your box plot, what you do is plot the minimum and the maximum. Do it up here above the number line you made. So I'll put a dot at the end point. That's about at 122. You can see it's pretty much right above 122. And then a dot above the maximum, 160. For these other three numbers, put vertical lines. So right there is 132, and then right about there is 141, and then 148.5 would be right about there. And then you turn it into a box because you draw the horizontal line that goes across the top and bottom, and you connect the box to the dots with what's officially called the whiskers. It's sometimes called a box and whisker plot. And this is your box plot. And that interquartile range, IQR, that is the width of this box. The 50% of numbers that are in the middle of this data set all live inside that box. And the lowest 25% and the biggest 25%, they're out here where the whiskers are. So 50% of my data happens right inside this box. And I can see where my median is. My median's shifted over to the right a little bit from the inside of that box. So if I had to estimate, I'd say that this data set was skewed to the left ever so slightly. because my middle is coming out over here. Yes,
Oh, well, I was gonna ask, the line in the box is the middle, right?
that's the median. So this is the minimum, Q1, median, Q3, maximum.
How did you get 148.5? I'm behind.
148.5 is the median of the bottom row. Yeah, this is, and the bottom row has 10 numbers, that's number 5, this is number 6. Their average is 148.5. And so I can, now that I have a sketch of my box plot, then I can just look and see which one of these it would be. It's clearly not A. It looks like B. It ain't C. And it ain't D. So B it is. Now that was us doing it by hand. It was already set up convenient for us to do it that way, and but it doesn't have to be. A lot of times it won't be. So we need to know how to get it done with some help from StatCrunch. So I'll show you now. I can open the data in StatCrunch because I have the raw data here. Right? Click the thing, open in StatCrunch. Now if I want a 5-number summary, I can go to Summary Stats, Columns, tell it where's my data, hit compute. Look at what I have. The minimum, Q1, Q2, Q3, maximum. That's all 5 numbers. So it'll give me, so see here Q3 is 148.5. And the median is just Q2, and then that's minimum and maximum. Okay, so I can get my 5-number summary like that. I can also have it just draw me the box plot. I'll go to Graph and Box Plot. I tell it where's the data, and I have to do some other options down here because it wants to. These people are weird because they want to draw it vertically. I don't know why. Tell it to draw it horizontally. If we draw it horizontally, then it makes more sense to us, at least me.
So after you hit variable horizontally in the compute?
Yeah. Yeah, I take variable 1, draw it horizontally, and compute. Yeah. And then kind of stretch it out, I guess, to get a good perspective. That way you're not trying to see what's happening inside this little square. And that looks pretty much like what we sketched by hand. I mean, the median is ever so slightly shifted over. Each of the whiskers seems to be roughly the same length. It's nearly normal. It's approximately normal, but I would be more comfortable if that median were more to the center. And that technique is going to come in handy on the next problem because these numbers are not in order, and that would be required for us to be able to to do it by hand. So I will just open this data in StatCrunch. And I will get my 5 numbers, stat, summary stats, columns. All I gotta do is tell it where the data is at. It's right there, compute. And now I've got my 5 number summary. The minimum is 120, Q1 is 125, and then the median is 137, Q3 is 142, and the maximum 150. These are the box plots they're offering me. I guess I'll see which one I should be looking at here. So I can go to graph, box plot. Data's right there. Draw it horizontally. And let me kind of make it bigger. Just one of the choices that's going to look like it. If you wind up with a bunch of boxes that really are virtually indistinguishable, you can just use the scale at the bottom to know if you have it right. Because the numbers on the box plot would need to match up with your 5 number summary. All right, everything after this is probability. So let's take a quick break. We're a little behind. It's 2:45, so I'm encroaching on our second break. And when we come back, we'll do probability. Excuse me. Are y'all caught up with the homework?
Yes.
Yes, sir. Yes, sir.
Oh, well, sorry. I'm doing number 6.
You're on number 6?
Yeah.
Did you already do 7?
No, not
Did
yet.
you see the process we just did with the?
Yeah, I
Okay.
was.
So that would help you get it right for sure. Intuitively, we know what a probability is. It's the likelihood that some event would happen or not happen, however you want to state it. Some things have a probability of 0, meaning they'll never occur. Some things have a probability of 1. Those things are guaranteed to occur. And so you can't get any more certain than guaranteed to occur. So all probabilities are between 0 and 1. A probability is a number between 0 and 1. Could be 0, could be 1. But it'll never be a negative number, and it'll never be more than 1. The number 1 corresponds to 100%. The number 1 is equal to 100%. They're the same number. And so, you may hear someone say, I'll give it 110%. Well, if it wouldn't make any sense to say, 110% chance I'm going to do good on that test. Because as big as it can go is 100. Probabilities are numbers between 0 and 1. We can have probability tables, just like we had frequency tables and relative frequency tables. But they will call it a probability distribution. And a probability distribution is nothing more than a relative frequency table. If I've got if I've got a trick coin, so I'm an amateur mathematician, or not mathematician, magician. I'm an amateur magician. I've got a trick coin. I can talk about events. I can talk about the probabilities of those events. Well, my trick coin will either land on heads or tails, but I don't know. I need to do an experiment to figure out what's the deal with this coin. So I'll flip it, let's say, 100 times. And 80 of them were heads and 20 of them were tails. But I flipped it 100 times. So 80 out of 100, 20 out of 100. This is exactly a relative frequency table. The right-hand column adds up to 1. I've got events on the left. I've got the relative frequency on the right. It's just now we've relabeled it Instead of classes, they're events, and instead of relative frequency, it's the probability. Otherwise, it's identical. So it would be telling me that 80% of the time the coin lands heads, and 20% of the time the coin lands tails. And me doing those 100 trials is called an experiment, probability experiment. Okay, well there's a basic understanding of probability. We know that this is a probability table because each of the numbers are probabilities, right? They're between 0 and 1. And when you add them up, you get 1 or 100%, whichever way you want to look at it. So if those two things happen, you have a probability table. Let's say I had some frequency table and it made the following histogram. Okay, there's my histogram. Let me recover what the frequency table would have been. What can these events be? Letter grade on a certain course. So there we go. And so this is some certain course, and how many students are in that course? Well, it looks like 20. So my relative frequencies would be, for A's would be 2 out of 20, and then for B's, 5 out of 20, 6 out of 20, 4 out of 20, and 3 out of 20. But I'm going to call this event, call this column events instead of class, and instead of calling this relative frequency, it's my probability. And the 2 out of 20, that's 10%. And the 5 out of 20, that's 25%. Six out of 20 is 30%. And this one is 16%. Oh no, wait, I'm doing this wrong. 20%. And 15%. And in either case, it should add up to 1. this adds up to 100%. This adds up to 1. And it's just a histogram. However, these bars, this one's got a height of 2, this has got a height of 5, and so on. Let me adjust my thinking that instead of the bars would have those integer heights, I want the bars to have these heights. So this first bar would have a height of 2/20. Or just 10%. And the second bar would have a height of 25%. 0.25. And this one's 30%. And when I do that, it makes the bars, they're all relatively the same height relative to each other. It would just be the scale that has changed over on the side. Instead of this scale over here being numbers 1, 2, 3, 4, 5, and so on, it would all be 1/20, and 2/20, and 3/20, and so on. And when I do that, I would need to make only one other adjustment based on my scores down here. Really, this should have been the other way, shouldn't it? It should have been FDCPA, go up, whatever. I want to say that that's just like 1, and here's 2, and there's 3, 4, 5, 6. And maybe I've got some kind of conversion table that'll help me convert back and forth. I'll know that between, I'll know that this right here corresponds to this event. And the reason I want to do that is because how wide is that bar? How wide is that bar?
Oh, 25%.
That's its height.
How much?
How wide is
How
it?
wide? Are you looking for the fraction into it?
It's not a fraction.
The ratio?
It's 1. The width is 1. That's how far apart 2 and 3 are. Each of those bars has a width of 1. Our histograms have to have bars all the same width. So somehow I've mathematically changed it to still represent all the same heights relative to each other, but now I've got all the bars to have a width of 1. Then I can do easy calculations of the areas of these rectangles. The area of that rectangle would be length times width, right? Where the length is 10% and the width is 1. So by having widths of 1, the area is equal to the height. So that rectangle has 10% of the area, and the next one would have 25% of all of the area of all the rectangles and 30% of all of the area of all the rectangles, and the sum of all of their areas would add up to 100%, or just 1. And we could say things like, so that was A, and this was B, and this was C, and I might wonder, I might wonder, what is the probability of getting a C or better? When I talk about probabilities, it'll be the probability of an event. So the event is getting a C or better. Well, you can easily see what the probability was for getting a C. It was 30%. So you could, what does it mean to get a C or better? It means you get a C or a B or an A. So it could be this, 30% you'll get a C, and 25% will get a B, and 10% will get an A. So how should I, that's looking at the table. If I looked at this picture, then if a probability is going to be, I mean, according to what we've done here, the areas are identical to the probabilities. So if you're going to get any of these, then shouldn't the answer be that it would be all of this area? So I would take this area and this area and this area, and that would be 65%. So the probability of getting a C or better is 65%. It was just the addition of the areas of those rectangles. And what we end up doing is, starting next class, we'll say, okay, let us move beyond this explicit histogram and recognize that the shape of the distribution here was approximately normal. And then let's just use the normal curve. Instead of this stair-step looking curve, we'll just use the smooth one, and it'll be about the same. But this is why we're using area as a probability, is that it amounts to this same situation. Here, I'll give you one more example. The mail. My mail carrier arrives on each day that the mail is delivered. On each day the mail is delivered, the mail carrier, like clockwork, comes between 1 and 2 p.m. Only thing is I don't know at all when they'll arrive between 1 and 2. All I know is that they will come at any randomly selected time between 1 and 2. Why do I have the height of this horizontal line at 1/60?
It's what the mark would be. It's like it's the hour mark. I don't know.
There's 60 minutes in an hour, okay? I want my I want, just like in the last example, the area of all those rectangles added up to 1. And what's the area of this? Is it 60? The length here is 60, and the height is 1 over 60. And the product is 1. Okay. So that's what told me how high it needs to be. This is called a uniform distribution. Then we might ask the question, like, what is the probability, P for probability? And then there's some parentheses that come after that P. The thing that goes in the parentheses is your event. Always your event. And maybe my event is that the mail carrier will come between 1, they'll come between and 140. Because dang, I got somewhere I gotta be, and I gotta leave at 140. So what's the probability that they're gonna come while I'm still here? So I have to leave at 140. I'm not gonna be there after that. And I would like to know the probability that they will come between 1 and 140. Well, if right there is 140, then the answer to this question would be that area. So you can compute the area of that shaded rectangle. It's just this dimension times that dimension. Say it.
140.
Now, this length right here, if it starts at 1 and ends at 140, that length is 40, right? So this edge is 40 and this edge is 1 over 60. 1 over 60. So 40 times 1 over 60 is the answer to this probability question. That's 2/3, which is about 67%. So there's about a 67% chance that I'll catch the mail before I have to leave. It's all about computing the area. And this is one of the easier ones you can do because it's just a rectangle. It's length times width. And for it to be a probability distribution, it must have been the case that the area under the whole thing was 1. And we did that. We did that by just fixing what the height would be. If they were going to show up at any random time in that time interval, then it didn't matter what the height ended up being, as long as they were all the same height. In the previous example, we had I did something down here with these scores so that the widths would all be 1 and the heights would correspond to the relative frequency. And we got an area of 1 underneath here, and it allows us to answer, all kinds of questions. I mean, probability of getting a D is just this column. This is where the D's are, and so there's a 20% chance of that happening. And a D or an F, that looks like it'd be a 35% chance, right? But isn't getting a D or an F the probability of not getting a C or better? If you do not get a C or better, then you got a D or an F. That's called a complementary event. And so we would say that all of the area, which is 1, or I'll put 100%, 100% of the area minus the probability of D or F, that's the same thing as the probability of A or B or C. Complementary events. And the key was that if I look at this event here, probability of A or B or C, take this event, take this number, this is a probability, the event is here. The probability of D or F, that's a minus. Add this number to both sides. If I add that number to both sides, then over here, let me write it up at the top. What it would end up saying, if you added this probability to both sides, you would have that 100% must equal to the probability of A or B or C plus the probability of D or F. Doesn't this cover every case? And it's equal to 100%. So this idea of a complementary event is sort of obvious after the fact. I mean, if you were to say, what's the probability that you get any of these scores, you're guaranteed to get one of these scores, right? And that corresponds to us having 100% chance. And this idea of taking 1 minus something, 1 minus this probability to get the opposite probability is a common thing that we do. So all that's happening is we're splitting it up right here. The total area was 1, and you had 65% of it here. You had 65% of it here. So if the whole thing is 100%, then naturally this other side would have to be that 100% minus 65%. Which is 35. Okay, now on the assignment, they're going to start us off with a question, and we should just rely on our skills at making a relative frequency table. Because that's really all that's going on here. I'm going to read their problem, and I'm going to create my relative frequency table that matches what's going on. So they tell me to consider these 2 different events, and that my frequencies are 223 and 226. The total would be 449. It is a relative frequency table, which is the same thing as probability distribution. But now I can answer probability questions associated with this experiment that they've done. They're asking me, what is the probability Really, this question is poorly stated. They're saying, what is the probability of a female being born to a couple using this technique? What they mean to say is that for the couples involved in this experiment, what was the probability of them having a female baby? We do not know how it would perform out in the wild. All we know is what would happen with these 449 babies. Nothing more. So let's be careful and make sure we know that when we're doing a probability question like this, it's only about the sample that's involved. In the future, we will extend our findings to the results about the whole population. So probability of having a female, right there. 226 out of 449. Nearly 50%. Rounded to 3 decimal places would be 0.503. Now they're going to ask me if this, does it appear effective in improving the likelihood of having a female baby. Well, one issue is that they didn't, the improvement is not well defined. I mean, it's 0.503, that's a technical improvement, but it's minuscule. You'll know that you'll know that the technique improved the likelihood if it's decidedly above 50%. Okay? Like in the 70s or 80s or 90% area. What's yours?
93.
Yeah. It would be something like that. They're not going to leave it ambiguous. It's going to be close to 50 or it's going to be in the 90s, something like that. Okay? So for me, it was not effective. It's essentially random. We already had that. All right, now I've got a survey of internet users. 3,555 of them said that they'll use social networking. But 1,359 said that they will not use social networking. So I have a grand total of 4,914 respondents. And I've made my probability table. And then here they have their question: what is the probability that a randomly selected person from the people that responded uses a social networking site? That would be the proportion of people that said yes. So I would go ahead and compute this number to a decimal with 3 digits. And I get 0.723. So about 72% of people are using social networking of the respondents. So I guess there's 2 ways to think about it. You could say, what percentage of my respondents are using social networking? Well, that's 72.3%. Or you can have the mindset that says, if I randomly selected one of those respondents, what's the probability that they use social networking? It's the same number. Because it's really the same idea. The internet quit. Is yours frozen?
Yeah.
Oh, man. Oh, there we go. Is it likely for a respondent to use social media? So here they wised up and they've used this word respondent. If they just said person, I'd have had an issue with it, because this is what it really is. This table that we built only deals with the people that responded to the survey, not just regular people out in the wild. Is it likely for a respondent to use social media? Yes. Why? Because way more than 50% of them are using it. All right, did we do good with those questions? Then the rest of them are all similar, 10, 11, and 12, and they deal with determining, is this table a probability distribution? And if it is, find its mean and standard deviation. Now, that's not the same thing as finding the mean of some numbers or finding the standard deviation of some numbers. It's the mean and standard deviation in terms of how it is a histogram, and there's some inflection points, not really, but the distance from the mean to the inflection point, that's the standard deviation. And it has a tougher calculation. We're not going to do it. It's not worth doing. I am going to show you the mean, though, but not the standard deviation, because the mean is going to get renamed in the future, and we're going to have a discussion board on it. The first thing they want us to do is to declare whether this table is a probability distribution. So it will be a probability distribution if those two things happen. Each of these numbers are probabilities. Well, they are, because they're all between 0 and 1. And do they add up to 1? I think so, yeah. So yes, this table does show a probability distribution. And what this table represents is that I've got a whole bunch of college students, a whole bunch of them. It's unknown how many. But I arrange them all into groups of 3. Here's a group of 3, there's a group of 3, groups of 3, as many groups of 3 as I want. And I go to each group and I want to just pose one question. This might as well say, do you take any online courses? To take one or more is to take any, right? So do you take one or more online courses? Do you take an online course? And then this column is telling me my different events that could happen. In that group of 3 students, none of them could be taking an online course. Or only one of them could, or 2 of them, or all 3 of the students could be taking an online course. And these are the associated probabilities. Okay. Now, the mean, it's the mean of this table. It's not the mean probability or anything like that. It's the it would be the mean of this table. And how would I compute it? It's actually very easy. You would take each one of these events. They have to be numerical events. You would take that event and multiply it times its corresponding probability. All the way down the table. Take the event multiplied by the corresponding probability. Event times probability. All the way down the table. And then you just add them up. That's the mean. So here I would have 0 times 0.108 plus 1 times 0.353 plus 2 times 0.393 plus 3 times 0.146. And you get some number. I'm not going to figure it out. I'll do it here in a second. But this is also called, in fact, it's more correctly called, the expected value. The expected value. If I go around to hundreds of these groups of 3 students, and I ask each one of them this, and I have. So I've gone around to hundreds of these groups and I've constructed this table. I've gone around to a bunch of groups, I've constructed this table. This is the computation of the expected value. I do this computation, I get some number. That number would then tell me, if I went to another group if I went to another group and wondered how many of them take an online class, it's the expected value. That's what I expect to happen. So let me get this number. I'm getting 1.577. Rounded to 1 decimal place, just be 1.6. 1.6 is going to be the answer I use. Now, that tells me that if I went to some other group of 3 students and asked, hey, how many of y'all take an online course? This is my expectation of how many it'll be. On the average, this is what I could expect them to say. Here's how you need to be doing it though. Not like this. This is just for reference. This is just what the expected value is. It's what the mean is. It's this times this plus this times this plus this times this plus all the way down the table. We're going to do it in practice just in StatCrunch. It's really easy. The place it's located at is kind of weird though. Okay. You have to open this table in StatCrunch. And you have to go to Stat, Calculators, and way down at the bottom, it's Custom. Stat, Calculators, Custom. It wants to know about the values and the weights. The weights are the probabilities. The values are the events. And then you compute. Look what it got for the mean, 1.577. The standard deviation, it's a little bit tougher computation. That's why I want to just use this calculator. Okay. And you can see it is a histogram. And it has constructed this histogram such that well, it could be, it's not true that the width is 1 all the time, but if I added up all the heights, it would add up to 1. Which is what their intention is. Look at this. Look at this statement they have down here at the bottom. This looks kind of familiar. It's a P for probability. I've got an event in here. It's coming out equal to an area. Look how they've got this shaded red. You know, this was 0 people took an online class. This was 1. This was 2. And this event right here is saying that the number of people who respond should be less than or equal to 2. What's the probability that 0 or 1 or 2 people were taking an online class? That probability is just the sum of these first 3 columns, 0.854. It's just the sum of these first 3 rows, 0.854. So we need to get real comfortable with this probability statement down here. Event, area. The event is in between the parentheses, and it comes out equal, the probability of that event comes out equal to an area. What's it going to say if I put 3 right here? It's going to be 1. Because that would be everything. It would just be the sum of 4 columns. What if I said that it's greater than or equal to 1? Greater than or equal to 1 would mean that there isn't anybody in the group that doesn't take an online class. All 3 of them take at least 1 online class. And you can see what it's painted red. That's just corresponding to the last 3 rows. And we're going to be using a calculator like this. Hop on. Anyhow, I've got my mean, I've got my standard deviation. They just want it to 1 decimal place, so 1.6 and 0.9. I'm done with this thing then. The mean, or expected value, same difference, 1.6. Standard deviation, 0.9. And then they have another question, just like this. And we do the same thing. This time it's about genetic disorder. They've got these probabilities. Now, if you look at that table, you can see that what immediately catches my eye is that these 2 numbers in the middle are the same. So both of those bars are the same height. And then these 2 bars are the same height. And then those 2 bars are the same height. This is a symmetric distribution. And it starts off at a minimum, it increases to a maximum, and then decreases. That's normal. So that's a normal distribution. In the future, we would just approximate this situation just with the normal curve. But here we'll do it in this discrete manner with just this histogram. Okay, yes. Those numbers do add up to 1, and they're all between 0 and 1, so it is a probability distribution. If I want the mean and standard deviation, I'll open the table in StatCrunch. Stat calculators way at the bottom is custom. I have no idea why they called it that. I guess because I can custom define what each column would be. The weights or the probabilities I compute. You could see that it's approximately normal now. I can see the mean, I can see the standard deviation. I could even ask all kinds of probability questions down here. All right, so my mean was 2.5, and my standard deviation was 1.1. So with that mean and standard deviation, because it was approximately normal, the empirical rule would apply. And I could say what's going to happen 95% of the time, let's say. So 95% of the time, if I repeated this experiment, 95% of the time, when I gather together these 5 males with their 1 child each, I could say that 95% of the time I'm going to have 2.5 plus or minus 2 times that standard deviation. That 95% of the time, the answer is going to be inside that interval. Well, 2 times 1.1 is just 2.2. So 2.5 minus 2.2, that would be 0.3. 2.5 plus 2.2, that's a 4.7. Well, okay, I didn't learn much. All I really learned was that 95% of the time, the 95% that's what's making this number happen, the 2, because that corresponded to the 2 standard deviations. And 95% of the time, the response of how many children inherited the genetic disorder, it's going to be bigger than 0, right? It's going to be more than 0, but it's going to be less than 5. So really, I would change this interval to be 95% of the time, somewhere between 1 and 4 children are going to have inherited it. Only 5% of it. So then that means only 5% of the time will it be either none of the children inherited it or all 5 of them got it. This is called a confidence interval. This is how they're doing the ranges on what's appropriate for a blood test or whatever. All right, last question. Households with a printer. Is it a probability distribution? I'm pretty sure. I mean, I could sit here and add that column up, see if it's 1. I think it is. Yeah. Open it in StatCrunch, get the mean and standard deviation from the custom calculator. So on the average, 2.4 households have a printer, but then that would be plus or minus something times the standard deviation of 0.97. I think they're going to want me to round to one decimal place, so 0.97 rounded to one decimal place is just 1.0. So on the average, 2.4 households. But I wouldn't expect it to be 2.4 every time. I need a little interval, some give or take, some wiggle room. And so you would say 2.4 plus or minus 1. Now that would happen to you 68% of the time. It's 68% of the time because I would be saying 2.4 plus or minus 1. That would be one standard deviation. If I did 2.4 plus or minus 2 times that standard deviation, that would be a 90. That would happen 95% of the time. And if I did 2.4 plus or minus 3 times that standard deviation, that would happen 99.7% of the time. That's nearly every time it's going to be in that interval. All right, well, we're done for the day. This type of stuff I've been doing on the side is where we're headed. That little calculator we were just using, we're going to use a different one next week for every problem. Midterm, do your midterm, and I guess that's it. I'll see y'all in a week. Yeah, what's up?
Can you help me with problem 6?
Problem 6.
I know how to do a stack crunch, but somehow I got lost on how to get Q1 and Q3.
Okay. Look at your top row
Top
of data. If you look at your top row of data, that's the lower half, because this is where the low numbers are, right? Now, there's 10 numbers there.
Yes, I'm sorry, I was looking at this half. That's my problem.
Okay.
But that number just not out. It makes sense now.
Yeah, the top row is the lower half.
Yeah.
So there's 10 numbers, there'd be 2 in the middle.
10 and 11. Add
Well, no, it's 5
and
and 6.
I'm sorry, 5 and 6 up here. The lower half would be 10 and 11.
No, 10 and 11 is the median.
Okay, teaching on this one, I'm sorry.
What's numbers 5 and 6 on this row?
144.
Okay, what's the halfway point between them?
146.
146. That is their average. Okay, so Q1 is 146. And do the same thing on the bottom row. Just pretend that all you have is that bottom row. And that they are numbers 1 through 10. Which ones are numbers 5 and 6?
1 through 10. 5 and 6. 166 and 169.
Okay.
So between those two, it's going to be 165.
They're 3 units apart. What's half of 3?
Yeah. Oh, that's the half. That's going to be the 167.5.
There you are. That's Q3. Okay, if I want Q2, then I need to consider all 20 numbers. And I'm finding a median, so that would be the halfway point between 154 and 158.
10 and 11.
That's no, those are positions 10 and 11. Yeah.
Okay. That's where I'm.
So the halfway point between 154 and 158 is
156.
that's the median.
Okay, thank you so much.
Yeah.
My brain's